There's an important aspect of finite difference formulas that we haven't considered yet that has to do with round-off error. So here's our forward difference formula. We have the derivative is equal to this difference quotient plus a term which is first order error in h as h goes to 0. But as h goes to 0, these two values in the numerator are getting close to each other. And so they suffer from subtractive cancellation. The condition number of that subtraction is equal to the maximum of those two values. So f of x plus h and f of x over the absolute value of the difference itself. And if we ignore the numerator for a second, as h goes to 0, then kappa, the denominator in kappa goes to 1 over, so I have to multiply and divide by h, so 1 over h times f prime of x times the numerator, which isn't very much concern to us. But what this means is that as h gets small, this condition number blows up. And so therefore, what we actually compute is the error is order h due to the formula itself. Okay, sometimes this is called truncation error or discretization, plus this kappa, which is 1 over h f prime, times the machine round-off. So this is the round-off contribution. And you can see one of these gets smaller as h goes to 0, but the other one gets bigger as h goes to 0. And so eventually, as h gets small enough, the discretization error becomes smaller and the round-off error dominates. And so what you can actually observe, if you do an experiment, is that as a function of h, if you take the log of the error in the finite difference formula, I'm sorry, this would be log h then because it's a straight line. So you would see a straight line of slope -1, right? That's the discretization phase, and then +1 thereafter. So at this side, discretization dominates. Then there's a break-even point, and then the round-off dominates. And in fact, it's pretty easy to see that if you have an O of h error, which is approximately equal to a 1 over h times some other constant, c2, times epsilon, right? Then you'd conclude that h squared is a constant times epsilon, or h is a constant times square root of epsilon. And so this break-off point is where h is approximately root epsilon. Which means, right, so that's the h where you get the lowest error overall, and since the error is proportional to either h or 1 over h times epsilon, so the best error is then order square root of epsilon as well. So that means that only about 8 accurate digits are possible using this formula. That's one of our motivations for going to a higher order formula. So if we said f prime of x equals some formula plus an error of h to the p for pth order accuracy, well, the formulas all work the same way. They have a bunch of constants times function values in the numerator, divided by h. And because h is going to 0, the stuff in the top must be going to 0 as well at the same rate. And so you still have a kappa which is on the order of a constant times 1 over h as h goes to 0. And so therefore the total error looks like, let's say, one constant times h to the p plus another constant times h to the minus 1 times machine epsilon. If you put those two in balance, right, you find that if you set these two equal to each other, you find that hp plus 1 is approximately some constant times epsilon machine. And that means that h is on the order of epsilon to the 1 over p plus 1 power. So that's the best h. And then the best error is best h to the p, because it's a pth order method. So that's the order of epsilon to the p over p plus 1 power. So when p is very large, that's almost epsilon. So for instance, if you use a fourth order method, right, it's order epsilon to the 4/5, which is pretty close to epsilon. You're getting most of the machine accuracy. So there are two good reasons for using these higher order formulas. One is that you achieve the best result for a relatively larger value of h, which means that you don't need to use as many points to cover an interval. And the other is that you are not as stung by round-off error if you can use a higher order formula. All right, so another thing we want to be able to do is to approximate more than the first derivative. So what about second derivatives? Now, it might seem that the answer is pretty obvious, right? Just apply the first derivative twice. And you can do that, of course, but it's not quite the best thing to do. So for example, let's say you use a centered difference. So first we do our centered formula to get the first derivative, because we want an accurate formula. We want a second order formula. So this is our minus 1/2, 0, 1/2 formula. Okay, fine. So that gives us f prime. But now to get f double prime, right? F double prime, and I guess I need a new symbol maybe, so I'll use a double circle, depends on 3 known values of f prime. Right? But each of these depended on 3 values of f. And so you end up using 5 different values of f to find one value of f prime, which is acceptable. It might be okay, but in fact you can do better. And the way you do better is to go back to the paradigm that we used. So it's better to use interpolate by a polynomial, differentiate it, but now we differentiate it twice, and then evaluate. So if we do that, let's say, for example, the most famous one is to use, again, one neighbor on either side. You get a parabola. You take the second derivative of the parabola. It's constant. So if you evaluate that at the middle point, you get that f double prime of ti is equal to f of ti plus h minus 2 times f of ti plus f of ti minus h over h squared, and then the error in this formula is second order. So now you see we have an h squared in the denominator for the second derivative. That's going to happen for any formula we have for the second derivative. And then you could increase the order of accuracy by putting in more points to the left and to the right. You might have to do that near a boundary, for example. And all the same comments apply. Same comments apply as to round-off error as before. So it's a pretty straightforward extension of the finite difference idea. And of course, to figure out what this order of accuracy is, you can use Taylor series as we did before. So finally, the last sort of generalization to mention is that sometimes we don't have equally spaced points. How about arbitrary points? And an arbitrary derivative? Well, you could always compute the interpolating polynomial, differentiate it, solve for the weights. You can do that over and over, but there's a nice systematic iteration or recursion for doing that, known as Formberg's algorithm. It's quite short, and it's provided as code in the book. So whenever you need to be able to do these kinds of formulas on points that are not equally spaced, it's easy to just call for the weights and do so.